Hello class, and thank you for watching. In topic 1.6, polynomial functions and end behavior, you will learn to describe the end behavior of polynomial functions using limit notation. We'll begin by first describing what an end behavior is. The end behavior of a function describes how a function is going to behave as it moves infinitely to the right or to the left. In other words, the end behavior is what happens to the values of y, which is the same thing as the notation f of x, as x increases or decreases without bound. So looking at those two directions, let's look at what the limit notation will look like. The left end behavior describes the values of the function y. In other words, as the x values again decrease without bound, the y values are going to do something. They're going to either again increase or decrease, or they're going to approach a specific value. For polynomial functions, since we're focusing on polynomial functions, it's either going to point up or point down. And if you recall from algebra 1, we used the notation, arrow notation then. We use x approaches negative infinity, and we said that the values of y, or f of x, were going to approach either positive or negative infinity. Okay? Now, don't copy that down because I'm going to erase it right now. What we're going to be using instead of this notation, we're going to use a limit notation. So to describe this behavior in this course, we're going to use this notation here. And in order to say that the values of x are going to decrease without bound, we're going to say that the values of x are going to approach, using this arrow right here, to negative infinity of f of x. And this is going to equal to something. Okay? It's either going to equal to positive infinity or it's going to equal to negative infinity. Now the right hand behavior just simply states the opposite. As the x values increase without bound, then the y values of f of x are going to do something. They're going to either go all the way to positive infinity or decrease all the way to negative infinity. And instead of using the arrow notations, the way to describe this is simply to say that x is going to approach positive infinity. So negative infinity means that the x values are decreasing, again, on the left side. Positive infinity, x values are increasing to the right side. So let's look at this and let's describe what's going on here using this notation. So let's start and describe the end behaviors of the following polynomial function. Let's begin by first looking at the left end, okay? The left end. Well, you can see again, this left end is pointing upwards. So as the values of x decrease without bound, the values of y of this function are increasing because it's pointing upwards, and those y values are getting higher. Right now, this y value is 4, this y value is 5, and because it's pointing up, it's going to be 6, 7, and on and on and on. So as our x values decrease, our y values are increasing without bound. To describe this behavior using the notation that we need to know for this course, we're going to write this notation as this. So instead of using the arrow notation, using limit notation, we would begin by writing the limit as x approaches negative infinity, and that the notation again is written like this. And then on the side, we would write f of x, and what is that going to equal to? Well, in this situation, since the y values are increasing without bound, then that means that they're going to approach positive infinity. So this notation is describing this end behavior there. Now to describe the other end behavior, this one right here in red, well, in this situation, we're now looking at the right end. So those are going to be the places as the values of x increase without bound. Well, what are the y values doing? Well, the y values of the function, again, are also pointing downward. So they're also, well, they're not also, but they're decreasing. Okay, so the values of f of x decrease without bound. So the limit notation for this description would just simply first change that the x is approaching to the right. So we use positive infinity, the same f of x. But instead of it equaling to positive infinity because it's pointing downwards, we just simply use negative infinity to describe that the y values of the function are decreasing without bound. Let's look at the next example. So for this example right here, on the left, as the x values decrease, notice that the y values at the arrows pointing downwards, so the y values are also going to decrease. Again, this notation here is because we are looking at the right end, okay? And saying that f of x equals to negative infinity, that has to do, this right there has to do because it's pointing downwards. The graph again is going down, so the y values are getting lower and lower every single time we pick numbers that are getting closer for x, that are getting closer to negative infinity. And then for the right end, we just simply change the statement to say that the x values increase. So that would change the limit notation to x approaching positive infinity of f of x. And since this again is pointing downwards, the y values also decrease, so this is also approaching negative infinity. Let's go to the next page now. Let's look at other examples, but this time let's look at examples without the graph, okay? Now, in order to determine the end behaviors of a polynomial function without the actual graph, is that we're going to use what's called the leading coefficient test. So we use the leading term, the term with the highest degree, okay, and see what the leading coefficient is and what the degree is to determine the end behaviors. Now, the polynomial function, so let me write this down. The polynomial function is the easiest way to find the end behaviors on the right side first, okay? Now, the right side goes upwards, okay, goes to upwards infinity, or sorry, let me use the right term here. This is supposed to be positive infinity. So the right side goes to positive infinity if the leading coefficient is positive, or the right side goes to negative infinity if the leading coefficient is negative. Having picked what's going to happen on the right side, then we can determine what's happening on the left by seeing what the degree of the leading term is, the degree of the entire polynomial. The left side is going to go in the same direction as the right if the degree is an even number, and it's going to go in the opposite direction of the right if your degree is an odd number, okay? So let's start with some very basic ones. So let's look at this example right here, okay? So we want to write a limit statement for the behavior of the polynomial function, okay? So let's write the limit statement first. So we have the limit as x approaches negative infinity of f of x. We want to know what that equals to, and what is the limit as x approaches positive infinity of f of x, okay? We want to first start on the left side. I'm sorry, on the right side, like I mentioned, on the right side, which is this one right here, okay? So we want to begin by first looking at what's happening as x goes to positive infinity. What is the y values going to? Well, to determine that, all we have to do is look at the leading term, that number right there. If that number is positive, then the y values are going to go to positive infinity. That's it. So on the right side, your answer is going to be positive infinity. Now, to figure out what's happening on the left side as x approaches negative infinity, what's happening to the y values? Well, for that one, you now simply look at this number right there. If that number is even, then it would be the same answer. It will be positive infinity. But if this number is odd, then it's going to be the opposite answer, and it's going to, in this case, it will be negative infinity. So there's your answer. So this is the limit notation for the end behavior of this example A. Let's look at example B now. So for this example, let's write this first, and we'll figure out what's going to equal to. That's your left end. This one is the right, and let's see what's going to happen on these. So for the right, as x approaches positive infinity, okay, we're going to figure out what happens to the y values by looking at this number right there. Well, since that number is positive, that means that the right end is going to go towards positive infinity. So positive infinity. Or just infinity. You have to write the positive sign, just infinity. Now, to figure out what's happening on the left side, we now look at this number, and if that number is an even number, which it is, then the y value behaves the exact same way. This is also going to be positive infinity. So there's your answer, which means that I don't have enough information about the graph, but it just simply means that the right end is pointing upwards and the left end is pointing upwards. And since this is x to the fourth power, then that means again it's going to probably go down, and it should technically, because it's to the fourth power, it should probably touch the x-axis 4 times. Okay, 1, 2, 3, 4, or it probably just touches it 1 time and it's tangent at that one place. Okay, but this is what we know for sure because of that information right there, that the left end and the right end are pointing upwards. Okay, now let's look at this next example right here. So for this example right here, we have that h of x is equal to 3 minus x to the 5th power, and we need to identify again the end behaviors using limit notation. Oops, can't forget this. Okay, so we need to figure out what's happening on the right. Now pay very close attention to this, because this one has 2 terms, and we're only worried about, let me erase this right now, the leading coefficient. Okay, the leading term. We only care about the leading term. Well, if you recall from previous lessons, the leading term is going to be the term that has the highest exponent. So among this is 3x to the 0 power, and this is 5x to the 5th. Well, 5 obviously is bigger than 0. So our leading term is going to be this one. It's going to be negative 1 x to the 5th power. And that's all we have to worry about, that one term right there. So now that we have the leading term, we can now focus what's happening on the right. So using the leading coefficient, again, this value right there, since that number is negative, that means that the right side is going to approach negative infinity. So this is the answer for the one on the right. And to figure out what's happening on the left, I'm going to now look at this exponent up there, and since this exponent is an odd number, it's going to do the opposite. So it's going to go towards positive infinity. And that's your answer. Let's see, let's do one more example. This example right here has a lot of terms. It has 3 terms, and we need to first identify what the leading term is. So we'll look for the term that has the highest exponent. So this has exponent of 2. Let me highlight in yellow. Exponent of 2, exponent of 3. And obviously this one doesn't have an x because that's x to the 0. So we only care about those two really. This one is higher than that one. So our leading term is going to be 1 x to the third power. So what's happening on the right side as x approaches positive infinity? Well, my y values, since this number is positive, is going towards positive infinity. And well, what's happening to the on the other direction as x approaches negative infinity, as it decreases without bound? Well, our y values, since this number is an odd number, is going to behave in the opposite direction. The left side is going to be pointing downwards, so negative infinity. So the left end is pointing down and the right end is going to point up. So there you have it. So in this example right here, we're going to write that the limit as x approaches negative infinity of f of x is negative infinity. And on the right, which means that x approaches positive infinity, the y values are pointing upwards. So there's your limit notation that represents this. Let's look at some more difficult problems, things that are not written in polynomial form, but instead of factored form, okay? So here we need, again, still the same thing. We need our leading coefficient, okay? I'm sorry, we need our leading term, not the leading coefficient, the leading term. The term that's going to be at the very beginning, or that should be at the very beginning. Well, to figure that out, we can start by first figuring out the degree. The degree, again, remember, is the sum of all the linear factors. So right here, I have 1. Let me rewrite this as x plus 0 to the first power. I have an x minus 1 to the third power. And I have a negative x plus 6 to the first power, okay? So to figure out what the exponent is going to be on the leading term, I simply add up all my factors. So 1x plus 0, 3 x minus 1, and 1 negative x plus 6, that's a total of 5. So the degree of this is going to be 5. 1 plus 3 plus 1. And I don't add this one right here because this one doesn't have an x. It's the x to the first power, which is the x plus 0 to the first power. So that's that. Now that's my degree. Now to figure out what the leading coefficient to my leading term is, the number that I'm going to multiply this x to the 5th, all I do is simply add every single leading term here, okay? Including this scalar. So I multiply, not add, I'm sorry, I multiply every single one of these leading coefficients. So I'm going to multiply a positive 2 with a positive 1 with a positive 1. Let me write the leading coefficients on each one. Well, this is a negative 1. And when we multiply those together, 2 times 1 times 1 times negative 2, that's going to be a total of negative 2. And again, we're not adding. I misspoke. I meant to say multiply. We are multiplying those quantities together. So now that we have the leading term, we can figure out what's happening on the right side, positive infinity, by looking at what this value is here. Since this value is negative, that means that the right side is going towards negative infinity. And for the left, since this number is odd, it's going to do the opposite. So positive infinity. So our answers are that as x approaches negative infinity, the y values of f of x are going to go towards positive infinity. And as x approaches positive infinity, the right side is going to go towards negative infinity. So there's your answers. So let's do one more similar to that. That's in factored form. So for this one right here, to figure out what the leading term is, Remember, we're going to need a leading coefficient, an x, and then an exponent. To figure out the exponent, we just simply add up all the linear factors. And right here, well, there is an x plus 3, but 6 of them. So this would be a degree of 6, since there's no more x plus or minus anything else. No more linear factors than that. And to figure out what the leading term is going to be, I simply multiply the leading term on each factor. So here I have negative 2 times 1x plus 3, and then I have another 1x plus 3. So again, I have 6 of these. So this 1 times 6, that's going to be 1. I'm sorry, this 1, a total of 6 times. So 1 times 1 times 1 times 1 times 1, and then times the negative 2, that's right here. I missed one. Okay, that's going to be a total of negative 2 when I multiply those quantities together. So on the right, now that we have the leading term, I can now look at the leading coefficient, and since it's negative, that means that the right side is going to go towards negative infinity. And on the left, since the exponent is positive, then that means that the left side is going to go in the same direction, again towards negative infinity. And I always write the left one first, even though I'm always doing I'm always calculating and identifying what's happening on the right first. I always write the left one first and then the right one second. It really doesn't matter though, as long as you understand that this notation, because it's going towards negative infinity, is the left, and this notation is for the right. Okay. All right, let's go now to the next page. And let's just practice again this with a little bit more longer ones. And let's see how the end behaviors of these functions, look like, okay? So for this one, again, because it is in its factored form, let's find the leading term. And we need the leading coefficient of our leading term and the degree of our leading term. Let's start with the exponent. The exponent part is easy because all we have to do is simply add up all of our linear factors. So this right here is 1. X to this x plus 0. This is x minus 4, but there's 2 of them. And this is x minus 5, that's only 1. So 1 plus 2 plus 1 more. That's a total of 4. So the degree of this thing is going to be 4. And to figure out what this number right here is going to be, we just simply multiply all the leading coefficients. So this negative 3 times this positive 1 times this positive 1, that's a total of negative 3. So the right, the y values are going towards negative infinity. And on the left, your y values are going in the opposite direction because this again is positive. I'm sorry, not positive, even, because that's even, so the left and the right again behave the same. Just like the last one. Let me go back to the last one. Just like the last one again. This number was even, so these two ends behave the same. So let's write the limit notation now. So the limit as x approaches negative infinity of f of x is negative infinity. Now we have the limit as x approaches positive infinity of f of x. That's also going to be negative infinity. Let's just do one more example like this, okay? So right here, g of x is equal to x squared, x plus 3, and 2 minus x. So x squared, x plus 3. And let's write this one backwards. I like to have the x in the front, so negative 1x plus 2 to the third power. And let's figure out what the leading term is. So we're going to have an x to the 6th power because the linear factors add up to 6. So 2 plus 1 plus 3, that's a total of 6. And for the leading coefficient, we're going to multiply the leading the leading coefficients on each term. So we're going to multiply these numbers. So -1, there's an invisible 1 here, and there's an invisible 1 here. So this invisible 1 times that is 1, and times that is -1. So now we can describe what's going on the right end first. Sorry, I put -infinity, I meant to write +infinity. So on the right, the y values are going towards -infinity. And on the left, your y values are going in the same direction, -infinity, because again, this number is even. So let's now write this as a limit notation. And there's your answer. Okay, now let's use this idea and let's again reverse engineer again this concept in order to graph a sketch of a polynomial function with the following end behaviors. So for this example right here, for example A, on part A on example 4, notice again, the first thing would, and I'm working on this so you can define and again know the difference between this and this. This is why I want you to practice to reverse engineer this. So you can recognize again that the first one, the one in purple, is referring again to the left end. So on the left end, as x approaches -infinity, means that as the x values decrease without bound, the y values of this function are going towards -infinity, so they are going to decrease. So on the left end of this function, the graph is going to go down. So the graph is going to look like this. Now, what's happening on the right? Well, again, reverse engineering this again, you have to be able to understand that this, as x approaches to infinity, means the right end. So on the right end, your x values again are increasing without bound. So they increase without bound. The y values here are also going towards -infinity. So they are decreasing as well. So that means that the right end, the graph is going down. So a sketch of this graph, a very basic sketch of this graph, if I just simply use a U, will look like this. Okay. This would be a very basic graph of this. I can make it curve more and have places again where it curves up and down several times, make it look like a M. I can continue making it look something again with more curves like that. But very basically again, it would just simply look like a parabola, a negative x to the second power basically. Okay. Now, let's talk about again what has to be true about this. The one thing about functions, again, polynomial functions, where the left and right end behave again in the same direction, they're both pointing up or both pointing down, is that these type of functions where the left end and the right end point down doesn't necessarily mean that we're going to cross the x-axis, because this graph can go all the way down here and we can see again that it doesn't cross the x-axis. So not every one of these can necessarily have an x-intercept. But the one thing that all of these graphs where they're always pointing in the same direction, whether it's again downwards or, let me flip it upside down real quick, or upwards like that, okay, and let me move up right here, is that the one thing that they are going to have in common is that they're going to have an absolute extrema. Every function where the two ends are always pointing up or down, they're always going to have an absolute extrema. In this situation, had they been pointing upwards, this point here, okay, or somewhere in my example, this point right there would be an absolute minimum. If it curved again other places, again, there will have to be a point where one point is going to be an absolute minimum for sure. What's not guaranteed is that it's going to cross the x-axis for sure. That is not guaranteed. But what will be guaranteed is that these things always have an absolute extrema, either an absolute minimum, or if I point this back in its original position, upside down, and I move it down here, it will have an absolute maximum. That is for certain. Okay, it could happen again that it does in fact cross the x-axis. Okay, that could happen, but not necessarily true that it's always going to happen, because as you see right here, this still satisfies this condition that both the left and the right end are pointing downwards. So let's write that. If the limit of negative infinity of f of x is equal to the limit as x approaches positive infinity of f of x, which in other words, I'm just simply stating that if the right end of the function equals to the left end of the function, then the function is going to have an absolute extrema, guaranteed. Okay, whether that's an absolute max or an absolute min will depend on where the ends are pointing. If they're pointing down, then we'll have an absolute max, and if they're pointing up, then we'll have an absolute min. But it will definitely have one. Where that value is, we're not interested in right now, but just understand that it's definitely going to have an absolute extrema. And let's now finally do our last example for today. So for this example right here, again, this notation means that we're looking at the left end. So as the left end decreases, without bound, the values of y are going to approach negative infinity, so they're also going to decrease. So the left end is pointing downwards. And as the x values increase without bound, so the right end, which is again this one, fix this on your notes, that should be a plus sign right there. This will also increase. So as the x values increase towards infinity, the y values of f of x are going towards positive infinity, so they're also going to increase without bound. So this end is going to be there. Okay. Now an easy, very simple way to connect this is to connect this again with a straight line. Okay, with a straight line right there. I can curve it a little bit. I'll just do a little curve right there. Okay. So this is a semi-basic function that connects these. Okay. And let's see what's going to be true about this. Well, the extrema part is definitely not true, because there's always going to be a point on this end that's always going to be lower than anything else. So there's not going to be an absolute minimum, and the same thing over here. There's not going to be an absolute max. There could be relative mins. I can make a curve up and down, and I can have this point be a relative max and this point be a relative min, but it's not going to be the absolute min, nor is this going to be the absolute max, because there's always going to be points that are going to be higher up here and lower down there. Okay, so there is no absolute extrema, that's for sure. Well, notice what it does do, regardless of how many times I connect these and how many times I curve up and down. The one thing that does happen is that it always crosses the x-axis. So functions, polynomial functions, where the end behaviors are pointing in opposite directions, are always guaranteed to have an x-intercept. Okay, at least one, like this one right here. It could curve up and down and have several, but for sure, you're guaranteed to have at least one one x-intercept. So that's always guaranteed. And again, the same thing would be true again if I flip this. So if I flip this upside down, look, well, in this situation, it looks exactly the same. So there's no reason to flip it. But if I was going the opposite direction, what I meant to point out, okay, if this end was up here and this end was down here and it looked like this, again, the two ends are pointing in opposite direction, and yet it's still going to touch the x-axis for sure, all right, regardless of how many times I curve up and down. And like I mentioned earlier, error will not have an absolute minimum. So let's write this down. So if the limit is equal to the opposite limit as x approaches to positive infinity of f of x, okay? So if the left hand side equals to the opposite of the right hand side, okay, f of x is going to have at least 1 0. Again, assuming that these things are polynomials, which I didn't, again, clarify the first time. I'm assuming here that this is a polynomial function, okay? If it's not a polynomial function, then we're talking about different else. But since we're talking about polynomial functions in this section, it's all about polynomials, then this is going to be true, okay? That every time that we have a function where our limits are going in opposite direction, we know that we're going to end up having to cross the x-axis at one place, at least one place for sure, okay? Where that position is, well, we would need to know exactly what that function is so we can factor it and see where those values are. Okay, that concludes the notes for tonight. If you have any questions, please send me a message through email or through Parent Square. And like I always, I appreciate you watching, and I hope you have a great night. Good night.